All right. So I think this is working. Hello? Yeah, I can see volume and such. Sorry. This is a recording to go with the beginning of Unit 2, so Introduction to Solutions. So it's a recording. There's none of you guys here, so you can't answer my questions. But as far as class, I'm not taking classes this block, but I'm teaching Earth Science B as well as your chemistry class. So you guys are my kids at Hope. You are talented, smart, and capable of success. You have dreams for the future, and you will climb to reach those goals and dreams every day. So this really doesn't apply since nobody's here. But today we are going to talk about some important vocabulary related to solutions and some factors that affect solubility. And these factors are also something you're going to test and experience in your lab for this unit. Okay, so this is an organizer that really covers a lot of stuff that we talked about last semester. All right, so we talked about pure substances versus mixtures. Mixtures are things that can be separated. Then we got into even some more detail as far as types of mixtures and homogeneous mixtures where you can't tell the different parts from each other were one of the types of mixtures, and that's where solutions fall. Solutions are one type of homogeneous mixtures. Right? Solutions that you're familiar with are going to be things like salt water. You can't see the salt, but if you drink it, you can taste it. Same thing with sugar water, right? Those are solutions. Other solutions include things like maple syrup. You really can't tell the parts of the maple syrup apart from each other, okay? So just know that solutions are a type of homogeneous mixture. So, two major vocab words related to solution. A solution always has a solute and a solvent. The solute is the substance that is being dissolved. So kind of like what we're adding. The solvent is what does the dissolving. So most solutions that you deal with are going to be a liquid and a solid. Not always the case. It could be two liquids. Yeah. All right, so typically speaking, you have a solid that you're adding to a liquid. The most common solvent on the planet Earth is water. All right, so the solute is what you're dissolving into solution. So salt in water, sugar in soda drinks, which is in water, or the carbon dioxide that's in the soda drinks. All right, the solvent is that outer part, the part that's actually kind of holding the solute in. And that would be, say, the water in your salt water, the water in soda. Right? Other liquids can be solvents too. It's just more often than not, water is the one you deal with. All right, so some important vocabulary to know is the word concentration. Right, so the concentration is the ratio of solute to solvent. If something is really concentrated, it's going to have a large amount of solute to solvent. Okay, if something has a low concentration, then it's going to be mostly solvent and very little solute. Okay, couple of words related to concentration. Something that we call that has a low concentration, it is a dilute solution, whereas a solution that has lots and lots of the solute, and in fact, if it gets to that point where it has the maximum amount of solute that substance can actually hold, we call it saturated. Right, so it's completely full. If you were to add more, it wouldn't dissolve. If you want to experience this, my suggestion would be take some salt and water. Keep adding the salt and stirring it. Add a teaspoon at a time. Stir it up, and then stir it until you can tell all of the salt has disappeared. Right? It actually hasn't disappeared, it's just dissolved. Right? And keep doing that. Eventually, you'll hit a point where you add another teaspoon of salt, and no matter how much you stir, that salt won't dissolve. When you reach that point where you actually have some of the solute that can't be dissolved into the liquid, we call that solution supersaturated. So it has more than the maximum amount of solute that it can hold. All right. So that's the major vocab you need to be familiar with. Make sure that if you're taking a quiz, you're doing your lab, make use of those vocab words. Okay? So, conditions that affect solubility. Solubility is the ability to be soluble, right? So how well things dissolve. And this is affected by several different things. All right, so solvent, solute. Water has a certain amount of salt that it can dissolve. All right, and water also has a certain amount of sugar that it can dissolve. It could be different amounts for the salt and the sugar based on when you hit that supersaturated state. Okay, so depending on what you are using, that can affect how solubility works. The surface area of what you are trying to dissolve can affect the rate of solubility. So think about it this way. What do you think is going to be easier to dissolve faster, a cube of sugar or granulated sugar? Okay, so surface area definitely affects the rate of dissolving. And this is something you are actually directly going to test in your lab. Temperature also affects the rate of dissolving and how much. Right? Warmer liquids can dissolve more than cold liquids. Right? They also tend to dissolve things faster. And again, this is something that you will see and observe in your lab, this unit. And then the last thing, pressure. So the more pressure you put on a substance, the more it will either dissolve or not dissolve something. So just to give you some graphical representations, oops, just kidding. So this is actually related to this first one, type of solute and solvent. Right? There's a general rule when it comes to what you can combine to make things dissolve. Like dissolves like. Right? So water, so I'm going to talk about the bottom first. Water is a polar compound. This is something you probably discussed in biology, but if you remember, you've got your H's and your O, and if you remember from last semester chemistry, oxygen is much more electronegative than hydrogen. Right? So hydrogen's way on the left side of the periodic table, and oxygen is way on the right side of the periodic table. So you've got a huge disparity in who wants to take the electrons more. Right? But this is a covalent bond. So what tends to happen with water is the electrons spend more time around the oxygen. The oxygen's kind of an electron hog. So that makes the oxygen end slightly negative, and the hydrogen end, this kind of like weird S thing, is for the fact that it's not a full charge. That makes the hydrogen end of the molecule slightly positive. Okay? So polar solvents, like water, are going to dissolve things that have charges on them, that have either full charges, like an ionic compound, or partial charges, like other polar molecules, really well, because the charges will interact with each other. Right? The positive end of the water will be attracted to the negative end of a polar molecule, and they'll interact really well. Okay? So salts, so table salt, sodium chloride, is called salt, but salt is actually a generic term for any ionic compound. So magnesium chloride, iron oxide, sodium chloride, oh, we already talked about sodium chloride, sodium bromide, all right? Any ionic compound is going to dissolve in water really well. And then sugars are an example of a polar molecule. All right? It's not ionically bonded because it's carbons and hydrogens and oxygens, which are all nonmetals, but they are polar like water, so they dissolve really well. The opposite end of that, there are nonpolar solutes, all right, which typically are fats. or things very similar structurally to fats, they don't get along at all with the polar things, right? You know this from maybe seeing salad dressing. If it sits for a little while, it separates. It has the water part separate from the oil part. Okay, so polar and non-polar things don't get along at all. You can kind of force them to interact, but they will want to separate from each other. So if you have polar, non-polar solutes like fats, waxes, steroid is a type of non-polar molecule, you're going to want to use non-polar solvents like oil, then hexane and benzene are liquids at room temperature. Okay, so key thing here is just to remember that water is polar and it's going to dissolve salts and sugars really well because those are also polar or charged. And then non-polar things like oil, okay, is going to dissolve non-polar things like fats and waxes really well, right? You don't necessarily need to remember all of these individual examples. Just kind of remember a example of a polar solvent and a polar solute, and a example of a non-polar solvent and a non-polar solute. Surface area. So when a substance dissolves, the molecules of the solute have to be able to interact with the molecules of the solvent. All right, so the more molecules that can interact at one given time is going to increase the rate at which things dissolve. Okay, so if you think about it, if you have a cube of sugar, so here's my cube of sugar, versus a whole bunch of just sugar molecules, all right, just think about these pictures right here. The only molecules that are going to be able to interact with water on the cube are going to be the ones on the very outside. All right. Whereas here, all of these molecules, there's space in between them, so they're all going to be able to interact with the water. So the smaller your substance, the faster the dissolving will happen. All right. So if you can break it apart, that's going to help with dissolving. Temperature. So again, just so that you can have some visual information here, we've got, you can see on a graph here, we are dissolving potassium nitrate, which is a salt because you've got the positive potassium and the negative nitrate, dissolving it in water. So as water increases in temperature, the solubility, the saturation point, right? So at 0 degrees, you really could only dissolve maybe 8 grams of potassium nitrate in 0 degree water. Okay? Whereas at 10 degrees, you can dissolve 10 grams. And at 20 degrees, you can dissolve 15 grams. And at 30 degrees, you can dissolve like 22 grams. So you can see as the temperature goes up, you're able to dissolve more and more. You're increasing that saturation point. And last thing, pressure. So pressure really only relates to gases, okay? Because liquids can't be compressed. So changing pressure doesn't really change the liquid. So the best example here is with a bottle of pop. You can also think of this as a can of pop. Whenever you open it, you hear that, like that pop and the fizz. There's gas escaping, right? And that is because the pressure inside the bottle here is higher than the pressure in the air. So when you have that higher pressure, you're able to dissolve more of the gas. Once you release that pressure and it drops, a bunch of the gas gets released into the air, and that's why you hear that pop, that fizz. Okay, so high pressure makes it so that the gases are more soluble in the solvent. So high pressure, better solubility. All right, so the assessment. There are 2 questions here. You can, if you would like to, count watching this recording as, one of your extra credit half points that you can earn for attending classes, what you need to do is you need to email me these answers. So you need to email me what is the term for the ratio of solute to solvent in a solution. So the vocab term way back at the beginning. And then you need to answer the next question, how can you increase the saturation point of a solid solute in water? All right, do me a favor, answer both of these in complete sentences. And email me your answers if you would like to have this count as attending class.